Hello, we continue our journey in standing waves or stationary waves. They have different names, but they're the same thing. So, like before, you have, let's say, an incident wave traveling to the right. When it hits that wall, a reflected wave goes to the left, or different color, lah, blue. And you notice this black color wave, right? All these particles. This is the resultant stationary waves because of two waves traveling in the opposite direction. Of course, there's a definition for it and there are conditions for that. So make sure you know those things from the previous video. Okay, so you see, eventually this part also becomes stationary wave, and then it's just node, antinode, node, antinode. There's always one place with maximum amplitude. There's always one place where nothing's moving at all. It's just pretty much sitting there. That's what we call a node. Okay, so uh, there are ways to think about this. In this video, we're going to look at a case study of standing waves on a string. And this is the very fun part, because if you know any kind of music or musical instrument, the reason why a music instrument can make noise is because of a standing wave or stationary wave. Okay. So let's take a look at this first beautiful video. Okay, this is a guitar string. So let's start over here. Okay, the pause lah, just a very quick snapshot. You can find this on TikTok, you can find this on Facebook, wherever it is. But if you want to go listen more, go follow this guy. It's called Acoustic Trench. Very nice, this fella, Acoustic Trench. But anyway, so that pay attention to the patterns in the waves, the strings. Look at all these patterns. Do you know all these were there? Maybe not, maybe you did. But what we're going to do now is, maybe not the guitar yet, let's go back to the basics of a stationary wave on a string. So if we have some setup like this in the lab or anywhere else, what you usually have is some weight on the one end of the string. So this is a pulley. This weight here is just to create a tension. Tension lah, you make how tight is a string. Okay. And in musical instruments, they usually knobs to make the string tight. That's the same thing lah. Okay, but here we don't have knobs. Then on one other end, you will have what we call a vibrator, which will create the frequency in the wave. So what these experiments do is, usually you change the vibration frequency here. So what you do is, maybe you start at 45 hertz, you bring it up, you see, oh, it's flat, then you go up some more. Oh, there's a standing wave here, so 61.5 hertz. Okay. There's like 4 antinodes. You keep going, wow, very big. You keep going. So basically, you're searching for where the stationary wave appears. Wow, this is a... So, you know, we get the point. You slowly drag it around. You see, whoa, this one has a 6 antinodes. Notice how the ends are always fixed. It's just in between that's doing all this wavy stuff. It's flat again. Oh, then another stationary wave, flat. Oh, another one. So how do you know when these things appear? Is there a formula to it? Not really. Wow, this one has many. So if you put this at 171 hertz, you see lots and lots of antinodes. Okay, so we're going to learn the physics behind this. When you change the frequency, when do these stationary waves appear? When do they not? Why other times it's just a flat thing? Okay, so this is where you need to grab a pen and we're going to do some drawing. So here's the variation of the string experiment. Okay, you have a string. You are changing the frequency with this vibrator right here. So this is your variable. Well, they are changing F. And then you will see what kind of patterns from a string. Now, if you get a chance to do this in lab, then good. So what's going to happen is, you will come to a certain point, certain frequency, where you will see a very nice shape on the string like this. Wow, that turned out kind of nicely. Okay, and then the bottom part, just to show that it's oscillating up and down, like zoom. So yes, there's a bottom part too. And then this part is fixed. So you see the string move like that. This is what we call a fundamental node. Fundamental. Mode, not node, sorry, mode. So whatever frequency where you see this thing appear, this is what we call the fundamental frequency, of course. fundamental frequency, which we call F0, F0 lah. Okay, and what would the wavelength be? Let's write down wavelengths and stuff, other info on this right side here. Well, wavelength, if I say this whole string's length is L, okay, then this L is actually half a wavelength, because you know full wave is usually like this but now it's only this part. So half a wavelength is L, the length of a string. So if I rearrange it, then I will have lambda equals to 2L. That is the wavelength of the fundamental note, okay? 2 times the length of a string. Okay, so that's the fundamental note. What happens if you crank the frequency up a little higher? Maybe you start off here with 100 Hertz. Sure, let's do that. Okay, so that's what fundamental note. Then as we crank up the frequency, you will have something like this. So you have the one wave amplitude here, an antinote here. Oh man, it's not symmetrical. Okay, and something like this. Ooh, now there's 2 of these loopy things. This is what we call the first overtone. Okay, overtone. And yes, oh, I forgot to label the nodes and antinodes. Here is a node, 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 and of course, antinodes here lah, where the amplitude is the maximum. Here only got 2 nodes, 1 antinode. Very simple. So how would the frequency relate to the fundamental node? Good question. This is times 2, because before that is, you know, 1 lumpy. Now there's 2 lumpy things, loopy things. So now your first overtone frequency will be 2 times of your fundamental frequency. So this is kind of like times 2. Times 2. Okay, and you get that. So if you use 100 Hertz at first, then this one becomes 200 Hertz. Some people call it harmonics higher. So in musicians, you say, oh, it use the higher harmonic, the first harmonic, the second harmonic, the same thing. And the length, okay, so the length here is now, oh, it's a full wavelength fit into a string. Yes, very nice. So now your length will be a full wavelength. Let's just call this lambda 1. Why not? This one called lambda 0. Okay, so L equals lambda. Very nice. Very straightforward. Let's keep going. Draw more and more until your page runs out of space. What happens when you come next? Well, this one here actually has 3 sections. This is our second. Oh man, this is not very curvy now. Second overtone. That looks something like this. Okay, and then of course there's the corresponding negative or positive amplitude in dotted line. Okay, to show that it's moving. And you have all the nodes here. Node, 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 antinode, antinode, antinode. Okay, take a guess. What's the frequency of this second overtone? F2. F1 is 2 times. So this one should be 3 times, because now you see it's 3 sections here. So 3 times of your original fundamental frequency F0. So if you take the original, you times 3 it, you'll get this. And this one we call, if you calculate it, it will be like 300 Hertz. Okay, so you see it's just getting higher and higher frequency. And how are you going to write out the length for this one? So the length of the string now is divided into 3 parts. How would you write that out? 3 sections. You can say, oh, this is 1 wavelength. So it's like 1.5 wavelength. So 1.5, or you say 3/2 of a wavelength of your wave. Okay, if you rearrange this, is lambda 2 by the way, then you have lambda 2 equals to 2/3L. Okay, how do you know this? You look from the beginning. Also, there's also a relationship for these wavelengths and lengths. If you take the original length, wavelength here, lambda 0, if you times 2 over here, sorry, not times 2, I meant divide by 2, okay, you will get this one. Okay, see on the left side, times 2, divide by 2, because here is lambda 1 equals L. Yeah, right for you. Okay, so 2L become L. Then the third one, okay, now you divide by 3. Notice the pattern. Divide by 2, divide by 3. So here is times 2, times 3. Why is that? You may wonder. Well, here's a reminder. When you have a kind of wave on a string, for this experiment, we're going to assume the V is constant. We're not changing the string mass or string tension because here we tie to a wall. So if your frequency increase, your wavelength have to decrease lor. Okay, so that's why here on the left side you see times 2, times 3. Right side is divide 2, divide 3. Okay, I think we have one more to go. Okay, so let's draw the third overtone. You guess how it would look like? So we separate out into 4 now. So we have something like this. Zoop, 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 zoop. Oh man, that's a bit out of shape. Okay, then you have the corresponding other part, positive or negative amplitude. So now this is the third overtone. And of course, what frequency will you have? F3 will have 4 times, see, 4 sections on it of your original fundamental frequency. So if your original was 100 Hz, this would be 400 Hz. It's fair. Can I draw the arrow, purple arrow if I can? Ugh, times 4. Wavelength, same thing. So now you have to think of, okay, the length of the string. How many wavelengths are there inside the length of the string? 1 wavelength. Here, 1 wavelength. 2 wavelengths. Okay, so we'll just say L equals to 2 lambda. 2 wavelengths. So this is your lambda 3 already. So the wavelength lambda 3 will be the length of the string, but cut into 2 parts. Because you can fit nicely, 2 wavelengths fit inside there. And of course, this one is divided by 4 lah, from the fundamental wavelength. Here, I shall draw a bit like that. Okay, so this is our picture of all the overtones on the string. You can actually go more and more, just keep adding, and then you draw lah more and more, you just get smaller and smaller, all these loops. So what to remember is, every overtone we squeeze in lumpy stuff. But how do we call that? How do we describe that in English? Okay, so this is how you say this. So each overtone, you want to add half a wavelength. So you add half a wavelength. So that's why we say lambda over 2. So you squeeze in half a wavelength. Okay, half a wavelength is this one lumpy antinote. Then here you squeeze in one more. Then become 3 then 4 then 5, 6, 7, 8. Then you divide accordingly. And the second thing you need to know is, not all frequencies can be stationary wave or standing wave in a string, you know. You see this? 100 Hz, 200 Hz, 300 Hz. What happened to 150 Hz? You won't see anything. You will not see a stationary wave. You just see an incident wave just traveling back and forth the string, but it won't be stationary. It won't be standing there. So only very specific frequencies can form stationary waves on the string. In this case, based on the length of the string, or if I say a fundamental is 100, then you have 100, 200, 300. Those are the only frequencies that can exist for this string length, because you only fit a certain amount of wavelengths inside there. Aha. So how can we write out this point? So, wrong pen. Oops. Only. So only frequencies where your waves can fit. See, fit into the length of your string. So only frequencies where your waves can fit between 2 nodes. Okay, nodes are the ones that don't move, are allowed, and that is also when stationary waves are formed. So, and stationary waves are formed. So what happened to other frequencies where you cannot fit your wavelength inside the string? Well, you can just make a note here, kind of a fact. Other frequencies will not observe stationary waves. Later we'll see some more gifs about stationary waves and what happens when they are not in those overtone frequencies. Observe stationary waves. Okay, so these are a few facts, okay? So remember, each time you go up an overtone, you're adding half a wavelength, and only certain frequencies can fit inside a string. So you have those overtones, natural overtones of a string. Okay. Oh, I forgot to label this one. Let's go. Node, 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 node. This is a na 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 thing. Okay. Notice how both ends are always nodes for this string experiment because both ends are fixed, ma. One end fixed to the vibrator here. One end fixed to the wall. Fixed up. Okay, so let's look at some gifts to better understand this whole stationary wave idea here. Let's go back to our experiment here. So, like I said, this fella, wow, very nice. He did a slow-mo camera, flipping physics, awesome gifts. So the first one, if you see the fundamental mode, you just see one antinode in the middle vibrating up and down. Okay, and in this case, for this material, we have a fundamental mode of 15 hertz. You see here, 15. Then you go to your first harmonic, then you have two places where you have antinodes. See here, moving a lot. Here, moving a lot. And it's 30 hertz times 2. Then you come to number 345. Oh, see, everything's moving much faster as well. So you have now how many places? 1, 2, 3 places where you have antinodes. They're moving maximum amplitude, minimum amplitude, positive amplitude, negative amplitude, up and down, up and down, up and down. And other places like here, not moving at all. So that's 3 times of the original fundamental mode. So 3 times 15, 45. Then you keep going. What's this? 1, 2, 3, 3 times, 4 times, and you just keep going now. So this one is 1, 2, 3, 4. So you can keep going. So this is 4 times of the original. You say, miss, 15 times 4 should be 60. How come this one's 61? Well, experimental uncertainty lah. You know, in real life experiments, things work a little differently. And you can keep going. Oh, it's getting harder and harder to see because they're like so small. So what this person did was did another camera. But before that, I want to take note of one more thing. When I ask you about things in phase or out of phase, you see these two antinodes, this one here and this one here for the second one. If I put a point at this antinode and another point at this antinode, would you call them in phase or out of phase? Or what is the phase difference? You see, when one go down, the other one go up. So they're like that. Up, down, up, down, up, down. This is what we call a 180-degree phase difference. If they are together up and down, that one is 360 or 0 phase difference. Together, together up, together down. But if they're doing like this, then got phase difference also. You need to look and see how to think of phase difference. So every time you look at all these antinodes, there will be in phase and some will have a phase difference of 180. You see the in phase 180 lor? Okay, so the person make it easier to see by using a camera video trick. Okay, they basically blur it out so you can see how it actually looks like. Here you can see very clearly this is the loop that we are talking about. The fundamental mode, first overtone, second, third, and fourth. Okay, you can very, very clearly see the nodes and antinodes. So if you apply this to an instrument like the guitar we saw earlier, how does it actually sound like? So here's a guitar I have brought along with me for class today. Okay, a guitar is very much a standing wave on a string, like what we are looking at here. So if you just pluck a guitar, any string, you will get the fundamental mode, like the very first picture up there on my cursor here. Okay, so it's going to sound like, I don't know, you just pluck some random string lah. That's it for that string, that's the fundamental mode. Open string, that's what we call it, that's your fundamental mode. But how do you get all these higher overtone things? Well, in music, they're called harmonics. So you see this second one, it's like the whole string but chopped in two. So my whole string from here to here, half would be somewhere here. Okay, so if I put a little finger here, okay, this is my fundamental mode. If I put one finger here, like how I'm putting a cursor here, I can force the first overtone to come out. So it will sound like this. You hear it's much higher pitch. That's why we call a higher frequency. The frequency is 2 times higher. So that's me putting my finger right here. So fundamental, first overtone. Okay, lor. Then you can keep on going, lor. The third one, you see the picture here. The third picture, you chop the string into 3 sections. So 3 sections somewhere like this, I guess, because the whole length is here. So imagine you're just chopping up the string into 3 sections. So, okay, so the next one will be here. This will be your second overtone. And I can put my finger either here where the cursor is or put my finger here where the cursor is, and it will force this overtone to come out in the guitar very clearly. So I'm going to put my finger right here like the cursor. And this is how it sounds like. Even higher pitch. So fundamental, first overtone, second overtone. It's like getting higher and higher. This is your frequency increasing. Now I'm going to try one more. The rest will be harder because you see their amplitudes are much smaller. This one got 1, 2, 3, 4. So you chop the whole string into 4. So I'm guessing 1, 2, 1, 2, 3, and 4. Okay, so I'm guessing this overtone will be right here. Even higher. Okay. So fundamental is very low. This overtone is the third overtone. Very high, I need 4 times higher than the overtone. Than the fundamental mode. Okay, so I just play through all again. Fundamental. Fundamental you call 0 lah. Okay, sure. First overtone. Second. Third. You can keep going lah. Keep going up, up, up. You can do this on any string. And of course, people use this to play music long. Things like that. Okay, so that's all about strings. Any kind of string instrument or even light bulbs hanging from the ceiling, you can have these kinds of stuff. Okay, so yeah, just make sure you know what are notes, what are anti-notes, how to draw these kind of stationary waves, because they will ask you to, you know, draw the standing wave pattern, label your notes, anti-notes, and maybe calculate frequency and things like that. Okay, so to summarize, whenever you have a string, okay, your fixed ends must be notes like here. And then if you have your fundamental mode, then half a wavelength is fit nicely inside there. Then for the next overtone, you fit another half a wavelength, so it become one full wavelength, and then you go so on and so forth. Okay, remember just now I mentioned what happens if your frequency that you choose of does not fit into the string, such as this one down here. Wavelength of 51 Hertz does not fit on the string. Let me remove my camera first. There we go. So what happens when your 51 Hertz cannot fit nicely on the string? Well, then all you see is just a normal progressive wave just rolling around the string, or you won't see a nice standing or stationary wave. So that's all about stationary and standing waves on the string. Now the next part is going to be examples for you to look at in the next video, and the next subtopic, you can say, will be stationary waves in tubes. Ooh, fun stuff. Okay, let's go see some examples.